Hi everyone, this is Chen from PUC-Rio. So today I would like to share with you my recent paper about the issue of how this notion of quantum metric is actually influencing a large part of how we see the world. And what I mean by that is that the quantum metric of the valence band states in the semiconductor or insulator is actually influencing the dielectric and optical properties of the semiconductor, including, for instance, the reflectance, which influences how bright an object appears. Yeah. And also, my formalism is able to derive what I call the dielectric and optical markers, which can study these properties down to atomic scale individually on every lattice site. And these markers can be used to study the effect of disorder, which is very important in semiconductors. For instance, the rubies are red because you have some disorder inside, while the sapphire is blue is because you put some other kinds of disorder inside. Yeah. So to start, let me briefly review these optical properties of semiconductors and insulators, where they come from and how do we describe them. And it all started with the wave equation of light in semiconductors. Yeah, for instance, how the electric field obeys, how the oscillation of electric field, the propagation of electric field inside the semiconductor is described by the wave equation, which you see that speed of light is no longer just speed of light in a vacuum, but rather it is normalized by this dielectric function, which you can as well write it in terms of complex refractive index squared. Now, this dielectric function can be further written as 1 plus I times the optical conductivity divided by frequency. Or you can think of your media as a charge polarization that oscillates with time. And in this sense, you introduce this chi, which is what we call the charge stability. Now, in terms of this refractive index, there's n tilde, and it also has the complex. It's also complex and has a real and imaginary part. But the real part is given, gives this bending of the light when it enters a media, right? While the imaginary part gives the so-called absorption coefficient, which is basically saying that the intensity of the light will decay exponentially inside a semiconductor with a decay length that is determined by this absorption coefficient, which is basically given by the imaginary part of the refractive index. Now, by matching the electromagnetic wave at the interface between the air and the media that it enters, you can define what is so-called reflectance, which gives you how bright the object looks like, right? And it is basically given by this combination of the real and imaginary part of the refractive index. So the purpose of showing you all these formulas is to demonstrate that, in fact, all these optical properties can be expressed in terms of the optical conductivity, which is also complex. Yeah, because you see that epsilon is related by optical conductivity by definition in this way, and epsilon is given by n tilde, and chi is given by epsilon, and so on and so forth. And refractive index is given by n, and therefore all of them can be expressed in terms of this optical conductivity. And moreover, this optical conductivity, the real and imaginary parts are actually not independent from each other, but they are related by the so-called Kronos-Kronig relation. Yeah, so you really only need the real part of optical conductivity to determine all these optical properties of semiconductors. Yeah. Okay, now comes the quantum metric. Suppose you have a semiconductor that has a lot of valence bands and a lot of conduction bands. Yeah, and the valence bands are totally filled and conduction bands are totally empty. Now, because electrons are fermions, so you can construct a single valence band state by fully anti-symmetrizing this valence band states, which I call it N, where A1, A2 to AN minus just enumerates the number of bands that you have. So you put it in this fully anti-symmetric Slater determinant, then you can construct one single state for this valence band all the valence bands that respects the Fermi statistics. Now you take this valence band state and momentum k and product with itself at a slightly different momentum. And the modulus of this quantity, if you do a Taylor expansion, you can see that it is equal to 1 minus some coefficient multiplied by this small displacement momentum square. Yeah. And the coefficient in front is what we call the quantum metric. And intuitively, this is you can think of it as this this valence band state, no matter what, is a unit vector in the many-body Hilbert space, right? So it's pointing in some direction in this unibody Hilbert space. When you move to a different momentum, this unit vector is going to rotate. So if you take a dot product between these two vectors, it's always less than 1. Moreover, it is given by cosine theta, right? Where theta is the angle between these two unit vectors. And you know the cosine theta leading on the expansion is this quadratic. And also you can express this quantum metric, as you can see, it is given by some derivative due to Taylor expansion of this original state. And you can also use this formula to convert them into the original valence band state N and the conduction band state N. And then it's going to look like this. It looks like it's summing over all the valence band and conduction band states with a derivative on this valence band states. Now, why is this anything to do with optical conductivity? This is because it turns out that the real part of optical conductivity, if you write down the expression of it, which you can simply argue it from the formula of Fermi-Golden rule, you see that it is some constant times the frequency of the light multiplied by this kernel, which is essentially the matrix element of optical transition, and which is precisely the quantum metric. And then you have to multiply by a delta function that ensures the energy conservation, that the frequency of the light has to match the band gap between the conduction and valence band. So, and therefore, we see that the quantum metric actually determines this real part of optical conductivity. But previously, I have shown you that the real part of optical conductivity uniquely determines all the other optical properties, and therefore, we recognize that the quantum metric actually determines all these dielectric and optical properties I have shown you in the previous slide. Now, okay, so here I show the formula again. So what you measure in real space is actually the optical conductivity in momentum space, but integrated over momentum. So you have an integration over momentum here. And moreover, this real and imaginary part, as you can see, both are determined by the quantum metric, and the kernels are simply related to each other via the Kramers-Kronig relation, as I have mentioned earlier. So now you can put this optical conductivity formulas into the formalism of the so-called topological markers. Now, if you're interested in these details, in my previous videos about universal topological markers, I have explained in details what these formalism of topological markers work. So here I will not repeat it again. So if you're interested, please check my earlier videos. And the result is that you can get what I call the optical conductivity markers. So these markers mean that this optical conductivity can be unique, can be calculated individually on every lattice site R here on the lattice. And the calculation is given by this ACE, which is the projectors to the individual lattice eigenstates, and multiplied by the position operators depending on the polarization of the light. And also there's a Fermi function if you are at finite temperature. And once again, you see that this kernel of energy conservation also shows up as it has to be. And the real part also has this kernel as very similar. So once you have these optical conductivity markers, you can put them back to the formula that I showed you in the very first slide that converts all these dielectric and optical properties into optical conductivity. Yeah, and in this way, you can also map all this dielectric and optical conductivity to real space individually on every lattice site. Yeah, for instance, this dielectric constant, charge susceptibility, the refractive index, the absorption coefficient, reflectance, transmittance, all can be mapped individually on every lattice site. Now, this is nice because you can use them. So the hope is that you can use them to study some effect of disorder. For instance, ruby is actually made of the aluminum oxide, but with chromium impurities. Because without these chromium impurities, the aluminum oxide is actually transparent. But because of these impurities, you see that the color has been changed. But if you put in a different kinds of impurities, such as iron, titanium, then you got sapphire, which the color is actually blue. Yeah? So this means that the impurities can affect the optical properties in a frequency-dependent way. Yeah. So you can actually, so the hope is that you can use these optical markers to study these effects. However, to do this for a particular material such as ruby, then you need a very precise band structure tight binding model kind of calculation, a very sophisticated band structure to capture all these optical effects, which I have not done it yet, but rather as a proof of principle, I use a simpler models. There's a so-called minimal lattice model of 3D topological insulators that that describes the usual topological time-versal symmetric topological materials such as bismuth selenide, bismuth telluride, and so on, where the low energy part is simply described by a Dirac Hamiltonian, where these D vectors describes the momentum dependence of the Hamiltonian, and the gamma are the Dirac matrices where you choose this particular representation here. And these D vectors for these 3D topological insulators, they have this particular dependence. Yeah. And okay, then what you can do is you can go ahead and map this momentum space model to real space by a simple Fourier transform. And you will get some tight binding Hamiltonian defined on a cubic like this. Now the expression is rather lengthy, so I will not show you here, but if you're interested, the details are in the paper. And then you can put in some impurities and then use these markers to study the optical effects of this topological insulator. So here I show you the numerical results. So what I do is, let's say you have a cubic lattice, right? So you put in some potential impurities on a specific lattice site, which I show you red here. And the markers can study the optical properties on this lattice site and its neighbors. And in fact, you can study all the lattice sites, however far away it is to the impurity site. So in this specific project, I study the markers on the impurity side and one side away from the impurity side, the nearest neighbor side, which is marked as orange, and the second nearest neighbor side to the impurity side, which is marked as blue, which is the and here I show you all the color, all the optical and dielectric properties as a function of frequency on these three sides. For instance, in optical conductivity, the real part of it, so I study its frequency dependence in units of electron volt, and I study the optical conductivity marker on the impurity side and the nearest neighbor side and the next nearest neighbor side, which is the blue and the orange. Yeah. And you see that the optical conductivity on the impurity side, this red line here, is very much suppressed. Yeah. So it means that the optical conductivity on the impurity side is actually highly suppressed. But even if you just move one side away from the impurity side, and then it pretty much recovers to the homogeneous value, which is shown by this thin black dashed line. Yeah, and the second nearest neighbor side as well. So you see that blue and orange are more or less the same in all the figures, whereas red is very much suppressed. Yeah. So so you see, for instance, the reflectance as well. The reflectance on the impurity side is pretty much suppressed, and while on the nearest neighbor side, it pretty much has recovered to the homogeneous value. And I should also comment that you see all these spiky features here. Yeah, so all the figures has the spiky features compared to the homogeneous dashed lines. And this is because I do the simulation on a rather small lattice sites where the lattice eigenstates are very much discrete. And if you have a discrete eigenstates, then these optical transition is going to peak at this the transition between the discrete eigenstates. So you're going to show these peaks. But usually these peaks will be more moderate if you go to a larger system size to simulate. But of course, then numerically it will be more expensive to calculate. Yeah. So using these results, I kind of conclude that it seems like the impurities, it does suppress all these optical properties. Yeah. In some frequency dependent way. But the influence is very local because you see that once you move away from the impurities, it has pretty much recovered. And this is somewhat expected because insulators, they usually don't have a length scale other than just the lattice constant itself. It's not like metals. Metals have a length scale. If you put an impurity on a metal, then it's gonna cause a Friedel oscillation, where the length scale of oscillation is precisely the Fermi wavelength, right? But here you don't have Fermi wavelengths because they are insulators. So this seems to be fairly reasonable that the effect of impurity is very local. So to conclude here, first, I was trying to convince you that the quantum metric actually determines many optical properties of semiconductors and insulators, including charge susceptibility, relative dielectric constant, optical conductivity, dielectric function, refractive index, absorption coefficient, reflectance, and transmittance. Yeah, so it actually determines a very large part of how we see the world. And secondly, all of these properties can be mapped to real spaces of dielectric and optical markers, which can study the effect of impurities in the nanometer scale. And that's it. Thank you for watching. So if you have any questions, please don't hesitate to contact me.